So exponential growth and decay today. Tuesday, we're going to do something called logistics equations. And that will be when your quiz on chapter 7 is assigned. Okay, you'll have a week to do it. And it's take home, so it's not going to be in class. And then Friday next week, we will start chapter 8, and we'll have a few days of chapter 8 stuff. I am also looking at doing some possible study sessions. Unfortunately, due to our wonderful social distancing and things, we're not going to be able to do them here, but we'll do them on Zoom. Okay. What I'm thinking at this point would be Saturday the 24th, probably at like noon-ish. The following Wednesday, when during my office hours, so like 12:30 till whenever. And then May 1st, Saturday, May 1st. So a couple chances. If you can make it to one or more, great. I just want to make that opportunity available. Excuse me. So I'm thinking we've probably looked at exponential growth and decay in like chemistry classes and other places. So hopefully this will be pretty straightforward. Of course, we're going to look at it with a calculus twist, right? So just in general, the differential equation for all exponential equations would be in the form dy over dx, or sometimes it's dy over dt because exponential growth and decay depend on time, is equal to some constant times y. And so if we solve this differential equation, we would get y equals, some constant a times e to the kt. And a is simply our initial value. Or y sub 0. So oftentimes we get the information we need just from the equation, or just from our initial information. To write the equation, that's what I meant to say. All right, so if we're talking about exponential decay, and most often we talk about radioactive decay, again, the initial differential equation might be dm over dt is equal to some constant k times m, and in this case, that constant would be negative. If you think about it, so change in mass with respect to time is some negative constant times mass, because we want it to be decay. And so e to a negative exponent goes to 0 as, in this case, time goes toward infinity. So we need that negative exponent for decay. And again, with radioactive decay, most often we talk about the half-life. How long does it take for half of a given quantity to decay? True story. Oh my goodness. All right, so we have the half-life of radium-226 is 1,590 years. Find the formula for the amount of radium-226 that remains after T years if you start with 100 milligrams. So our general equation, the mass at any time t is going to be our initial mass times e to the kt. So we've got a few variables we need to solve for. We need to solve for t and we need to solve for k. With the information that we're given a time, so we can solve for k right away. I know that I will have 50 milligrams after 1,590 years. So if I solve to get k, divide by 100, and oh, surprise, surprise, I get a half when I'm talking about the half-life. How do I get rid of E? What's the inverse operation for exponential function? ln, logarithm, natural logs. Yes, I'm going to take the natural log of both sides. And when I take the natural log on the right-hand side, that exponent comes down out in front, and ln of E is just 1. So that's another fact that they expect that you will know on the AP exam. And then I can divide by 1590. Excuse me. On the AP exam, if you were working this problem out, I would not find a decimal approximation. Don't round in the middle of the problem. If you need to round, round at the end. So using things like your last answer key or the store button. That's what lower left-hand corner, right above the, whatever, it's like the second button up, right above the on button, I think. STO. Y'all know how to use STO? Okay. Good, because I don't remember. No, I know how to use. All right. So we've got our value for K. So now my expression I'm going to write T ln 1/2 over 1590. Which is kind of messy. Now, when I look at this, I think back to what we just said about exponential decay and how K is supposed to be negative. And K doesn't look negative to me. Right? However, ln of 1/2, if I use my law for logarithms, that would be the ln of 1 minus the ln of 2. And what is the ln of 1? 0. So ln of 1 is 0, so we have 100 e to the negative ln of 2 times t over 1590. And maybe you're happy. Now it looks negative. Now I think I'm okay. Now it seems to match what we had talked about before. Most often, this will not be written this way. Because there's one more thing that you can do to simplify it. Oh. All right. And the thing that you can do to simplify it, so we've got all of that already. We're good there. Is we can take e to the ln of 2. E to the ln of 2, e and ln are inverse functions, so they cancel each other out. So the way this is most often going to be seen is we're going to have 2 to the negative t over 1590. And the reason you'll see that most often in like a textbook, it doesn't take as much text to write it. Right? They're saving some money. But mathematically, that is equivalent and true. All right. The other, and there are other examples you can use, like population. We're actually not going to talk about population until next week when we talk about the logistics equation, because it models population more accurately over time than exponential expressions do. But interest and interest rates, most banks calculate interest usually on like a daily basis, but they could calculate it continuously, compounding it continuously. And again, it's an exponential function. It is going to be your initial value in your account times e to the RT, where R is your interest rate as a decimal, and T is time in years. So, you know, maybe you were fortunate and your parents invested $100 when you were born at 1.5% interest, and it was compounded continuously. On your 18th, and they kept it secret from you, you didn't know about it. And on your 18th birthday, they said, "Happy birthday, here's your account." How much money would you have in that account when you turn 18? It's a surprising number. You're going to be shocked. All right, so if I calculate that,
Wait, why is
it's,
it not 1.5 and it's 0.015?
so in order to use that function, I'll go back one slide here. The interest rate as a decimal. So if you use 1.5, that would be 150% interest, right? So that would be great. That would be even better. Just a little bit better. But yeah, it's because the interest rate we need to convert to a decimal. Yes, in 18 years, that account made $309.96. Yes. Now, if we didn't have to, if we did get 150% return, which again, that would be like crazy stuff. If we did 1.5 times 18, and hopefully, if you did this, you would say, "Wow, that really looks not right." You know, $532 billion. Maybe a little off. Okay, so just, you know, great question though. It's a good one to ask. $1,309.96. So when I took, I think it was Calc 2 in college, we did continually compounded interest. And on one of our exams, the question was, you know, the settlers paid the Indians X amount of dollars for New York way back when. If that was invested in an account that earned, and I don't even remember what the percentage rates were or anything, you know, what would the account be worth today? And it's almost as depressing as this. Oh.
I thought I saw some, if you invested in a penny, at the start of, or when Jesus was born or something, it would be like.
So,
Pretty insane.
yeah, so kind of that question, like if I gave you a penny today and 2 pennies tomorrow and 4, you know, and kept doubling it, how much would you get at the end of the month? And it's millions of dollars. It's yeah. So things that double and accumulate like that really accumulate quickly. 18 is going to be a interest problem, and it's going to ask you to compound it yearly first, which is just, you know, I equals PERT. And then part 7 is continuously compounded, and parts 2 through 6 are different compounding periods. That's just, to me, that would be kind of busy work to do. I just want you to see the difference if we compound it yearly or annually as opposed to continuously. Right. I do have your tests, and I will hand those back after I quadruple check that I've entered them in. So you'll have those in just a moment.